Hello everyone, welcome to another Watch Me Do Math video. Today we're going to be going over some problem solving or IQ test style questions or math questions from the BMAT 2018. Now, this video is going to be shorter than it otherwise would have been because following last video I realized the actual size of the video in covering an entire paper's problem solving would be inappropriately long. And it would also be exhausting for me to make another one of those. So I've chosen 8 questions, the first of which you see on the screen, that I think are interesting and provide value to you if I go ahead and cover them in the way that I usually do. So, to begin, for reference, by the way, these questions are questions 3, 7, 14, 16, 18, 23, 29, and 31. So, 5 employees swipe a card every time they enter or leave the office. The times for Thursday are shown in the table below. As part of a performance review, the manager observed the activity in the office between 10 and 12. Which employee was in the office for the largest total amount of time during this 2-hour period? Okay, so this question kind of reminds me of that Among Us map where you have the door logs. But anyway, let's look at this methodically. The first thing I want to do is draw a line. What I'm going to do is draw a line at 10 o'clock in each column and at 12 o'clock for each column. So firstly, I know that 12 is before these numbers, but after this number. So I'm going to write a 12 o'clock line here. This is 12 o'clock. And 10 o'clock falls between these two, and these two, and these two, and these two, and these two. So, knowing this information about the 10 o'clock and 12 o'clock, I think it becomes much easier to visualize sort of what the time that they spend in the office during the period where the manager is here, because you know that the manager is going to be here in between these two lines. So, as part of a performance review, the manager observed the activity in the office between 10 and 12, which was in the office for the largest total amount of time during this 2-hour period. So again, I think in calculating this, drawing out these lines was key to visualizing the data much easier. So if you have enter, the people are already in office here, so they leave 63 minutes after, and then they enter 18 minutes before 12. So this employee has 63 plus 18 is 81 minutes. Then they leave at 9:52. They enter at 11:23 and leave at 11:46, so that's 23 minutes. And then they enter at 11:55, and so that's 5 minutes until 12. 23 plus 5, well, that's obviously less than 81. I'm not going to calculate it because it's so obviously less than 81. We have Rob here, who spent 17 minutes in his first batch, and then 34 minutes in his second batch. That's 60 minus 26. And then 22 minutes in his last batch. So 17, 34, and 22 add up to 60, and this is 13, so 73 minutes. But that's not the most. Sana spent 10 minutes in the office, their first, between this 10 o'clock line and 10:10, and then they entered at 10:16 and left at 11:50, meaning that this period of time, from 10:16 to 11:50, this 34 minutes to 10:50, followed by 60 minutes to 11:50, 34 plus 60, was all spent in the office. 10 plus 60 is 70, plus 34 is 104. And so Sana at the moment has the highest number of minutes. And finally, Teresa left at 2 minutes after 10. And because she spent 30 minutes out of the office, we can immediately rule out Teresa because that means her maximum could not have been more than 90 minutes. So Teresa may have spent 90 minutes in the office, but that means it's impossible for her to have been first. So Sana was the answer. Sana is the one who spent the longest time in the office during the 2-hour period. Now moving on to the next question, question 7. The lift in the hotel I am staying in takes 3 seconds to move between consecutive floors, and when it stops at a floor, it remains stationary for a minimum of 9 seconds to let people in and out. 3 seconds to move between floors, stops for 9 seconds. A screen inside the lift, or 3 seconds per floor. A screen inside the lift shows the list of floors that it has been requested to stop at. When the lift moves after stopping the floor, it always stops next to the closest floor on its list. If 2 floors are equally close, it continues in the direction it was previously traveling. The door of the lift has just closed after I have entered it at floor 11 and added floor 4 to the list of floors to be stopped at. The other floors currently on the list are 1, 6, 15, and 24. Assuming that no further floors are added to the list, we are here. Assuming no further floors are added to the list, what is the minimum time that will elapse before the lift door opens at floor 4? Well, you know that the lift's algorithm to decide where it goes, firstly, you know that the door of the lift has just closed. It's going to travel to 15 because that's closer, taking 4 floors times 3 seconds is 12 seconds, stopping, adding 9 seconds, to 21 seconds of travel time, and then 6 and 24 are equally close to 15. The lift will continue upwards to 24 because it wants to move in the same direction. 21 plus the 7 seconds of movement make 48. Stopping at 9 seconds, you get 57 seconds. Stopping for 9 seconds, you get 57 seconds. And again, you don't need to write all these multiplications out. You should immediately be able to tell that it's 4 floors, 12 seconds, 9 floors, 27 seconds. Multiplying by 3 is an operation that you can do in your head after all. So you have 21 seconds, and then you add 27, 48. And then you add 9 seconds because it stops, and that's 57. And then it goes all the way back down to floor number 4. So going all the way back down is 18 times 3 is 54. 54 seconds plus 57 is 111 seconds. Stopping at floor 6 for 9 seconds, 120, and then traveling for another 6 seconds, the 2 floors to floor 4, 126 seconds. So what is a way you could have done this faster? Well, what I think is, after you have drawn out the initial diagram of the lift's motion, moving up and down a certain number of seconds is something that you should be able to calculate pretty fast. So you can just write at what time it'll be at a certain floor. So I would actually lay my work out like 24, 15, 11, 6, 4. I would lay my work out like this because I knew the direction it's going to take. It looks like this, 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 right? So I'm going to write it here at t is equal to 0, and so it's here at t is equal to 12 and stops 21, here at 48 stops 57, and then back down 111 stops 120, back down another 2, 126 seconds. Here, the arbitrary system of working I've created moves 1 to the right when it stops, just for the convenience in writing that I add 9 seconds, and it basically shows the time, the current value of t, starting at t is equal to 0, given the pattern of motion that the lift has. Alright, so let's continue. Going on to question 14. Among a group of 6 children, 2 belong to a football team. Philip says it is Roger and Kayla. Okay, this is PQRST. Four of the children correctly named one person and lied about the other. One person lied about both. The sixth person said nothing. So Philip says it is Roger and Kayla. Kayla says it is Philip and Roger. Roger says it is Kayla and Sam. Sam says it is Trista and Roger, and Trista says it is Ursula and Sam, and Ursula refuses to say anything. So we know for a start that one person lied about both. I'm not really sure what direction to take it. So okay, suppose that P lied about both, okay? If R and Q are not on the football team, then P, S, and T are all on the football team. So we know that's not true, because only 2 children belong to the football team. So I think the key is identifying which 2 will eliminate as many possibilities as possible from the other 5 statements, such that only 2 people remain, right? Or you want one that tells us which 2 people are actually on the team. So if PR was a lie, then we know that Q would be on the team, and if Q is on the team, then S is a lie, and that means U is also on the team. So knowing that Q is on the team, and U is on the team, and R is not on the team, we are also told that T is on the team, so we know that's not true. We get another contradiction. So what I think is happening is that we're going to have to write this out a bunch of times and decide by elimination, by testing the possibilities, who are actually on the football team. Because I'll be very honest, I can't actually see a quick and clever way to do this. So given that we write out our working like this, we select QS as our 2 lies. That means S is a lie and R is a lie. And Q is a lie. That means R is on the team, U is on the team. If R is on the team, then P is a lie, correct? If R is on the team, then T is a lie. Oh, so if you look at this, this is the scenario in which everything is logically consistent. R and U are on the team. And if this is true, if this is the logical configuration that makes it such that you have one person who's lying, Roger is lying about both, double lie, and everyone else says one person who is actually on the team, that is R and U, we eliminated Kayla in every instance, and we eliminated Sam in every instance. And we know for sure that this means Trista says U is true and Sam is a lie. And we also know that it says R is true and Kayla is a lie, right? So if R is true, then that means everyone else is also following the rule that they name one person truly and lie about the other. And I think that means, I think it logically follows from there that if that's one setup that satisfies the whole system, then U and R must be the two people who are on the team. But I'm just going to check that because I'm not sure whether that logic holds. So for instance, if T and R are the two on the team, are the two that are not on the team, and R is removed, then you get Q and P being on the team. If Q is on the team, then S is a lie. But that also means that U or S, that also means that U must be on the team, so that can't be true. And finally, if U and S are not on the team, then S is not on the team, Q must be on the team. If Q is on the team, R must not be on the team, and that means T must also be on the team. You get 3 people, and that's not valid. So I think you can immediately say that the answer is R and U after you have found one set of answers which is logically consistent with the statements given to you. Alright, so let's move on to the next question. Question 16. In a paint factory, large and small containers must be filled with paint. 2 pumps are available. The fast pump can deliver paint at 12 liters per minute, and the slow pump can deliver at 6. Kadu begins to use one of the pumps to fill a large container and the other pump to fill a small container. He starts at the same time, and when the small container is half full, he swaps to the other one. Both containers become full at the same time. Okay, intuitively, I think a large container is 100% bigger because of the idea that one of the pumps is 100% bigger. So let me explain. Oh, no. Maybe this is not right. But anyways, if I have some pump here, and the small container is half the size, right? That means the small container being half full you would have a quarter full large container. And switching this over to the fast pump means that you'd get a 3/4 full large container with a full small container because it takes double the time. So I think perhaps then the large container is only 50% bigger because a small container filled halfway with the fast pump or the slow pump means that you'll get one of these two sections, either a whole volume of the small container or half a volume of the small container, respectively. And as you swap, the opposite becomes true, right? So in the end, you get the 50% larger container. So it wasn't 100%. The main thing to keep in mind is that this is true because the restriction that you swap the containers when the small container is half full rather than after any amount of time ensures that you have as much time as it takes for the small pump to fill half a small container plus as much time as it takes for the fast pump to fill half of the small container, and this amount of time is constant. So whichever way you assume the small container starts, it will always end up being the case that the larger container is filled at each pump for a certain amount of time. So suppose the small container was 6 liters large and the large container was 9 liters large, it would take 15 seconds on the big pump, meaning 15 seconds of slow pumping, or it It would take 15 seconds on the slow pump, meaning 15 seconds of fast pumping. Hang on. Okay, so small t, the fast pump, small amount of time for 3 liters would be 15 seconds. And this same small t for the fast 15 seconds with the fast pump here means 15 seconds with the slow pump, or 1.5 liters, right? And then 30 seconds on the slow pump means 30 seconds on the fast pump for this one. So 30 seconds on the fast pump is 6 liters. Oh, that's right. This is inaccurate. So, in fact, I have proven my own answer wrong, that this should be 7.5 liters. Now the reason that that's interesting is because it is a valid problem-solving technique with these kinds of puzzles to put your own numbers to it, as long as they are not some random convenient number that allows you to abuse a special property of it, like of 1 or 0 or the like. Then putting numbers to these problems, which only works in the case that the problems imply that it's the same no matter what the actual sizes of these containers are, for instance, means that you will get a valid result. So it's like doing an experiment with real values to see the pattern you find, right? You can use real numbers in abstract questions like this to make the calculation much easier. Alright, that's interesting. So I'm just checking this through in my head again. 3 liters at the fast pump, 15 seconds on the slow pump, 1.5 liters. 3 liters on the slow pump, 30 seconds on the fast pump, 6 liters. Yes, okay, that's true. Now we move on to question 18, which is the 5th question of today. Three-year-old Arthur has a junior Skittles set and contains 4 red Skittles, 4 yellow Skittles, 3 balls, and a felt mat. 6 of the 8 Skittles are placed on the spots. There are 2 extra in the case of loss or damage. The balls must then be bowled from behind the line at the other end of the mat. How many different arrangements of red and yellow Skittles are possible on the 6 circles on the mat? Okay, so what I think is that you can view this in the sense of 2 yellow Skittles are excluded, 2 red Skittles are excluded, or 1 red and 1 yellow Skittles are excluded. And in each scenario, when there are 2 of the same color excluded, you would have 4 of the other color and 2 of the same color in the board. Which are Skittles that can be arranged in 6 factorial, or 720 ways, meaning that there are 6 Skittles that you could put on the first hole, and then once you've removed 1 by placing it here, there are 5 Skittles you could put on the next hole, 4 on the next hole, 3 on the next hole, 2 on the next hole, until you're left with 1 that must automatically go in the final hole. It is through this idea of a factorial, 6 times 2 times 5 times 4 times 3 times 2 times 1, because each possibility creates a whole new set of setup of the Skittles, that we get this number 6 factorial. But you must also remember that the order in which the 2 yellow Skittles are placed down doesn't matter. So the yellow Skittles could go first yellow, second yellow, or second yellow, first yellow, and it would be the same to us. It would be the same to an observer. So given that you have these 2 unique yellow Skittles, or 2 unique red Skittles, R1, R2, Y1, Y2, you could have, there are 2 that you could possibly place down first, and 1 that you could possibly place down in the second position. So meaning that you divide this by 2 factorial for the fact that there are 2 red Skittles, and therefore 2 factorial orders of red Skittles that we could look at. And vice versa with yellow Skittles in this scenario. And then we also must account for the fact that the other color, which has 4 Skittles placed down, also doesn't matter which order we place down the Skittles of the other color in. If there were 4 yellow Skittles, for instance, Y1, Y2, Y3, Y4, and they were all unique, then there would be 24 ways to put them down in different orders by the same logic as we just worked out. So you could put any of the 4 in the first slot, and for each of those possibilities, there are 3 possibilities for the Skittles you could put in the second slot, because one of them has been vanquished in the first slot. And then, respectively, for each of those 12 possibilities of first and second Skittle, there are 2 Skittles remaining, one of which can become your third Skittle, and so on. So divide by 4 factorial in each case. And ultimately, this boils down to 6 times 5 divided by 2 in each scenario here, and the 6 and the 2 cancel out to get 3. 3 times 5 is 15, 3 times 5 is 15. Now, if you are familiar with the math behind this, there is no need to go to such explanatory lengths as I have done here. I am only doing this to make sure that you understand the math behind the combinations of Skittles that could be put down. So, in these 2 cases, the logic that I have used to get to this number of 15 combinations of Skittles when 2 yellow or 2 red are excluded thus has been explained clearly. And I'm going to shortcut around that during this explanation and just write from my understanding of the logic behind the red and yellow Skittles that in the case that we have 3 red and 3 yellow Skittles on the board, there are 6 factorial divided by 3 factorial, 3 factorial. Oh, this cancels to 6 times 5 times 4, and 3 factorial is 6, meaning 20 possibilities for 3 red and 3 yellow Skittles to be placed on the mat, meaning that our final answer is 15 plus 15 plus 20, or 30 plus 20 is 50. And that's our answer, 50. So to do this question quickly, you'd want to notice, all right, there are 3 cases. One of them is 2 excluded yellows, 2 excluded reds, and 1 excluded red and 1 excluded yellow. So in other words, you could have 4 red and 2 yellow, 3 red and 3 yellow, or 2 red and 4 yellow. And you work out the answer for all of these different numbers of red and yellow Skittles, keeping in mind that the answer for 4 and 2 is equal and equivalent to the answer for 2 and 4, whereas 3 and 3 are the only ones you need to calculate separately, coming to the final answer of 50 for question 18. So now we move on to question 23, which is the next one I wanted to look at. I use a 4-digit PIN with my bank cards. Each digit can be any digit between 1 and 9. I have set up a code such that the first and second digits are consecutive. Subtracting the first from the second digit gives 1. Okay, so that means you have A and A plus 1. The third and fourth digits are consecutive. Subtracting the third from the fourth digit gives 1. So you have B and B plus 1. And the first and fourth digits add together to give the same value as the second and third digits multiplied together. So A plus B plus 1 is equal to AB plus B. Interesting. What is the last digit of my PIN? Yeah, it seems like this is the answer. 1, 2, 2, 3. I'm not going to get into the algebra, and intuitively that was the answer that appeared in my head. I'm going to explain why now. So, suppose you have some 2 numbers that one number above and one number below must multiply to a certain number, right? In my head, I thought the place that this is most likely going to happen is when you have low numbers that are being added together, such as 1 and 3, or 1 and something, and 2 times something. I tried with another set of numbers in my head, namely 1, 5, 2, 4. like this. And I realized this is too big compared to the stuff we get when we add it up. And going down one more, again, we get the same problem. This is too big compared to what happens when we add these up. And so continuing to go down after testing things like 1289 or 1278 and noticing that always the number multiplying together in the middle is too big, I finally reached this answer of 1, 2, and 2, 3 because it is just right such that it fulfills the requirements of the question, because 2 times 2 is 4 and 1 plus 3 is 4, right? So the intuition here was that firstly, the first digit or the last digit the first digit must be 1, the last digit cannot be 1 due to the restriction that it is more than 0. Due to this restriction that it must be 2 or more, given that it's b plus 1, where b is at least 1. And the next key piece of intuition was that I needed to pull the numbers in the second half down such that the conditions could actually be satisfied. Otherwise, the numbers in the middle would never be enough to, would always be much greater than the first and last digits added together. And that got me to the final answer of 1, 2, 2, 3. So those were the, if you rewind and listen to that talk again, those were the two main pieces of intuition that allowed me to reach this answer without any calculation. So let's continue. Now we move on to question 29. Most board games require that 2 dice are supplied, with 2 identical dice having 1 to 6 spots on their faces, have opposite faces adding to 7. The 2 dice supplied with one of my board games are different. One has 0 to 5, with spots on opposite sides adding to 5, while the other has 2 to 7, with spots on opposite sides adding up to 9. Okay. This is a view of both dice together. Which one of the following could be another view of one of the dice? Well, something I like to do here when I see a question like this, especially about dice, is label the opposite sides. Dice presented in this projection, in this way, have a convenient way of doing so, because you can point here, here, and here to designate the back sides. That you would see in separation from the front side. So, for instance, this back side, this 5, 3, and 2, or this 4, 5, and 2, this one must be the 2 to 7 die, because if it was the first die, the 3 would be on the opposite side of the 2. So opposite to the 2 must be the 7, opposite to the 3 must be the 6, and opposite to the 5 must be the 4. And knowing that this is the 2 to 7 dice, we can say that this must be the 0 to 5 dice. The 0 to 5 die. So opposite 2 must be 3, opposite 4 must be 1, opposite 5 must be 0. So which of the following could be another view of one of the dice? We test each one against what we think is a valid view of the dice. 6, 3, and 2 cannot be on one corner because, as you can see, they're wrapped around in this shape. They are not connected at all 3 faces, so A is certainly wrong. 2, 4, and 3, however, this seems like a fair candidate because 4, 3, and 2, on this die at least, are connected together. On this die, they would not be connected together because they are connected like this. There are these 3 faces, but on this die they might be. However, if you turn the dice in your mind, you take this cube and you flip it such that this 2 comes down here, this 3 comes over here, then you find that the 4 is actually on top. as opposed to on the bottom. So you can tell that this dice is not going to be correct from the orientation of the dots on the dice, as well as the result you get when you flip this in your head. Now, here's one trick I have to help with the flipping of dice. Okay, so what you do is you take your 3 fingers with your thumb like this, your index finger up, and your middle finger out, right? And your other 2 fingers are recoiled. You let your thumb be one number. It points to one face on the die. Your middle finger points to another face on the die, and your index finger, your second finger, points to the top face of the die. And you keep track of the number that is represented by each of your fingers. So, for instance, 1 represents the side with 4, 2 represents the side with 2, and 3 represents the side with 3 dice. Holding your hand up like this, actually do it with me in front of your screen, and rotating your fingers around this way will lead you to a logically consistent view of the dice as if the faces had been rotated. Right? So, how do I mean? Well, if you rotate the fingers this way, for instance, your view will become something like this, where this is your thumb, this is your second finger, and this is your third finger, where this is your index finger, and this is your middle finger. To draw it out again, it would become something like this. So this is thumb, index finger, middle finger. And the numbers that are assigned to each remain the same. Or to do it even further, you would get something like this pointing off in the distance, this pointing somewhat up, and the third finger pointing somewhat this way. Right? So, in this sense, you would still get a valid cube, but the values would just be flipped as you have flipped them. So for instance, your thumb will have this 4 side on top. Your finger will have the 2 side here, and your middle finger will have the 3 side here. You can do this trick with turning your hands around any number of times, and you'll always end up with a valid way of drawing the dice, or drawing the die. So I hope that's helpful to some of you. But anyways, we have eliminated B as an option because the 4 was on top, where it is not in our actual understanding of the die. So now we look at this 5, 1, and 3. At first, I'd say yes, it seems correct, because 1 and 3 are at the same corner with 5, this particular corner here. So knowing that if you looked from this corner, you'd see something like a 5 in the bottom here, and this is the corner you're looking at. You'd see a 3 on the back side, which now looks like this, and a 1, oh, I've drawn this poorly. You'd see a 5, a 3, and a 1 on the bottom. So again, using my fingers as 5, 3, and 1, this time starting in this format, with my thumb, index finger, and third finger pointing towards here. Middle finger is 1, thumb is 5, index finger is 3. If I rotate my hand, I can see that this 5, 3, and 1 is satisfied by the sides that appear here. So option C must be the right answer. We can go about eliminating the rest of the options. For instance, we eliminate E because if you have 5, 5, 4, 3, taking your thumb here, your index finger here, and your middle finger on the 3 side at the back, turning it around this way such that the 5 is to the left of the 4, we get the 3 on the bottom and not on the top. So option E must also not be true. And finally, option D, I'm not sure how to describe why this is eliminated, but I'll let you know that my logic for it is that it's likely to be the case that putting this 5 and 6 on top, if you do the rotation in your head with this third finger here, index finger here, and thumb here, you'll notice that the line of the 2 dots here and here are tangent to your thumb. They don't go through your thumb. And as you tilt it, your thumb would end up here, right? Because your index finger, which represents 5, ends up here, and your middle finger, which represents 6, ends up pointing this way. But the thing is, the dots on this go in a line that goes through your thumb, so you know that this must not be true. Whereas we would expect the dots to end up here, tangent to our thumb, which represents that face of the die. And so option D must also not be correct. So I hope that strategy helps with you. Anyway, let's move on to question 31, which was the last I'm going to look at. Bruno was awarded 48 marks out of 80 for his coursework project. The maximum mark available for each of the 4 sections, R, D, C, and S, was 20. The smallest difference between the marks awarded to any of the sections was 2. This was between design and construction, which were his 2 best sections. The largest difference was 11 between design and evaluation. Oh, why did I write S for evaluation? Anyway, between design and evaluation. How many marks was Bruno's research section awarded? Okay, suppose we have his best 2 sections, D and C. We know that E is going to be less than D because D and C are the best. We don't necessarily know that C is better than D or that D is better than C. But because D is so much greater than E, for the purposes of figuring it out, let's first propose that D is the largest. If D is bigger than C by 2, and D is a maximum mark of 20, C is a mark of 18, and E is a mark of 9, as suggested by the fact that E is 11 less than D, then he is already at a mark of 38 plus 9 is 47, and so his research mark would be 1. This is clearly not correct. So what can we do that maintains this distance between D, C, and E, but awards marks to the research, such that the research is oh, wait, hold on a minute. Never mind. The largest difference was between design and evaluation, and the largest difference between 2 elements of a data set is the range. That tells us that the evaluation was the lowest, and so what we need to do is we need to increase R without increasing the overall score. So we'll take 1 point at a time from each of these and move it to R, adding 3 to the score, until R gets within the range of these 3. So first we have 19, 17, and 8, where research goes to 4, 18, 16, and 7, where research goes to 7. And this could be valid because R is within the range, but however, it means that the difference between these 2 is 0, which is not allowed. So finally we get 17, 15, and 6, where research was 10 marks. So, knowing that research was 10 marks, all of these add up to 48. The condition that the 4 marks are at least 2 away from each other is also satisfied, and the condition that the largest distance is 11 is also satisfied. So 17, 15, 16, and 10 satisfies all logical requirements, meaning that Bruno's research section must have been 10 marks. So that's the final question that I was going to do today. If this video helped you, please be sure to share it with your friends and subscribe to the YouTube channel. And until next time, which will probably be longer now that we're much closer to the test, I'm going to make one more video talking about my thoughts on the university entrance process and your place in university before I go. And that's it. Bye-bye.